Today I am going to tell you about this electric dipole, and in this class we will also discuss about the torque acting on a electric dipole when it is placed in a external electric field. And second one, we will also see the derivation of the amount of work done in rotating a dipole in external electric field. Okay, so let us see what is electric dipole. So first of all, we must know that when the two equal and opposite charges are separated by a small distance, then it is known as the electric dipole. So let us see. Suppose here we are having two charges. One is minus q and second one is plus q. And let the distance between the two charges is 2a. This is 2a. Okay, so here in this case we can say charges in an electric dipole, both the charges are equal but opposite in magnitude. One of the charge is negative charge and second charge is positive charge, and this length 2a is known as dipole length. So here we can write it 2a. This is dipole length. Clear? So if we talks about the definition of electric dipole, then how we will define it? So let us see. A group of two equal and opposite charges separated by a small distance is known as electric dipole. Okay, and the second definition about the dipole moment. So dipole moment we represent by this P. This is dipole moment. We can represent it by this is P. Okay, so what is electric dipole moment? This is P is equal to any one of the charge into dipole length, like this. So if we have to calculate the value of dipole moment, we will find it like this. P is equal to, this is Q into 2A, or we can say P is equal to Q into 2A. Right? Now, as far as the definition of dipole moment is concerned, we can define it the product of any of the charge, any one of the charge, and the dipole length is called dipole moment. It is basically a vector quantity, means it has some direction. So what about the direction? Because charge is a scalar quantity and the dipole length is a vector quantity. So as far as direction is concerned, so let us see, we are going to discuss here. So in an electric dipole, the direction of dipole moment is always from negative to positive charge. So here we can see that the P, direction of P is from a negative to positive charge. Okay, so this was the introduction of electric dipole, and now in daily life or in practically we can see that how this dipole is formed. So let us see the example of HCl molecule. So suppose we are having hydrochloric molecule. Okay, so here we can see that hydrogen is having one electron in its outer orbit, while the chlorine is having 7 electrons in its outer orbit. So we can write it like this. Now as far as the sharing of electrons or the formation of the molecule is done, so we can see that the hydrogen shares is one of the electrons, while the chlorine also shares one of the electrons. So there are 2 electrons between this. Now like this, the octet of the chlorine atom is also completed, and hydrogen is having first orbit only. In first orbit there are only 2 electrons which can be accommodated. So 2 electrons of hydrogen are also complete and 8 electrons of chlorine are also complete. Now because hydrogen is electropositive element and this chlorine is electronegative element, it have greater affinity, larger affinity for electrons. So this shared pair of electron is shifted towards the chlorine atom. Hence we can say, finally, what happens? The shared pair of electron shifts towards the chlorine atom. So that's why here the net charge becomes slightly negative. We can show it like this, delta minus, and here similarly we get the positive charge. So in this molecule, the shared electron is shifted towards the chlorine, while the positive charge, center of the positive charge, remains as it is at its position, where we can say the center of positive charge and the center of negative charge now are differed. So that's why this dipole is formed. So in this case, this is the explanation about the formation of electric dipole. So now in this case, we are going to see what is the expression for torque acting on a electric dipole when it is placed in external electric field. So let us see. I am rubbing this. This is first derivation. This is torque acting. Torque acting on electric dipole. So let us see, we are seeing this. This is the external electric field. Okay students, so here we are having a uniform electric field. It is represented by, its magnitude is represented by A. Now its direction is from here to here. If we place an electric dipole in this electric field, then we can see that, let us say, this is negative charge and this is positive charge. Okay, so this is a dipole. It is making an angle theta with the electric field like this. So one thing you have to remember now, because electric field is also a vector quantity and dipole moment is also a vector quantity. So previously I have told you that the direction of dipole moment is from negative to positive charge. So this is the direction of dipole moment and this is the direction of electric field. Okay, so theta is the angle between P and E. So here we can see that theta, this is angle between P and E here, right? Now what happens when we places a positive charge in the electric field? A force will act over it in this direction. We can take it like this. This is QE. Okay, and at the same instant, when we talks about the force acting on the negative charge, it will be in this direction. This is also QE. So now one thing comes in our mind, why this force is here and why this force is towards the left side. So let us say we have to explain it. So if we take two parallel plates, one is having positive charge, the second plate is having negative charge. Okay, so if we places a positive charge here, now electric field lines always moves from positive charge to negative charge. So we will have an electric field here in this direction. So now you can see what will be the force, where in which direction will the force will be acting on this charge, because this is negative charge, negative plate, so it will obviously attract the positive charge. Hence, the force on this positive charge will be towards this side or in the direction of electric field, right? So that is the reason. So the force acting on this positive charge is towards the electric field, and the force acting on the negative charge is towards the positive. Okay, now here we are going to see the torque acting on the electric dipole. Now when we say two equal and opposite forces, one force is this and second force is this, they are equal and opposite forces, so they will tend to produce a rotational effect on the torque. Okay, so this electric dipole, so that's why this dipole will be rotated like this. So here the torque will be, this is torque is equal to force into perpendicular distance, right? When the distance comes, this total distance is 2a, like this. So if this distance is 2a, this angle is theta, so this angle is also theta. So when we talk about this, this point is A, this point is B, and this point is C. Now when we talk about the torque, so torque will be equal to, this is force is QA, and the perpendicular distance between the two forces, that will be BC. Here we can write BC. Now what is the value of BC? This is because perpendicular and hypotenuse is 2a, and sine theta, as we know, sine theta is equal to perpendicular upon hypotenuse. So that's why this BC will be equal to, this is 2a sine theta, like this. So putting the value of BC, we will get torque is equal to, this is QE into 2a sine theta, like this. Now Q into 2a is P. P is dipole moment. So finally the formula becomes torque is equal to PA sine theta. Okay. So this is the formula for torque acting on electric dipole. And as far as vector form is concerned, because torque is a vector quantity, so we can also write this torque is equal to, this will become P vector cross E vector. So this is the vector form of torque acting on an electric dipole, right? So I think this article is clear to you all. Now second, we are going to say the amount of work done. So when the dipole is rotated in an electric field due to some external source, then there will be some work done. So let us see how we will calculate that work done. So this is second article, work done in rotating a dipole, rotating a dipole. Okay, so let us see, as we know, because torque is equal to, this is PE sine theta here in this particular case. This is the torque. Okay, so if we rotate the dipole by some small angle d theta, if d theta is, this is a small angular displacement, small angular displacement, right? So as we know that the small work done, there will be some work done. So the work done is always equal to this force into displacement in linear motion. But in rotational, when we talk about the work done is given by the product of torque and angular displacement. So here in this case, if we rotate the dipole by small angle d theta, then the small work done dW will be given by, this is torque into d theta, like this. So putting the value of torque, we will integrate this expression. So this will become dW is equal to PE sine theta into d theta, and we will integrate it from theta 1 to theta 2. So students, dear students, here we are taking two limits. Theta 1 is the initial angle and theta 2 is final angle. Okay, so suppose we consider that the dipole was initially at theta 1 angle. If it is rotated by up to angle theta 2, then these will be the limits, and when we solve it, it will become this is W and this is PA, and here it comes to be sine theta 1 then theta 2 and integration of sine theta d theta. Now what is the integration of sine theta? Mathematically it is the integration of sine theta is minus cos theta. So we can write it W is equal to, this is minus PA, it becomes cos theta to the power limits, this is theta 1 and theta 2. Okay, so putting the upper and lower limits, we will get work done is equal to minus PA cos theta 2 minus cos theta 1, right? And this amount of work done is stored in the form of energy in the electric dipole. So we can say energy stored in the electric dipole is this, U is equal to minus PE, this is cos theta 2 minus cos theta 1. Right? So this is our expression for energy stored in an electric dipole. Right? So these were the two small articles which I have taught you in this particular class. So today we will stop our class up to this topic, and in the next classes I will tell you something about other topics. So to see further videos, you can subscribe our channel on Sunrise Tutorials. Okay.